Welcome back. Let's do a few more predictions using our regression line. So data that included information on Y, the weight of the trash in pounds on the street in 1 week, and X, the number of people who live in the house, were collected. Fitting a simple linear regression model gave our equation Y equals 2.340 plus 11.30x. So it says use the equation to predict the amount of waste for a street with 0 people living on it. So we get Y is equal to 2.340 plus 11.30 times 0. So we get 2.34 pounds of trash. Okay. And is that realistic or could it be extrapolation? So it certainly could be extrapolation. We might expect that if nobody's living in a house, that they wouldn't generate any trash. But let's think about some other possible explanations here. So maybe this is something like litter that's blowing around on the street. Maybe somebody drove through and ditched their trash. This could be, maybe there's construction going on, so there's no one living there right now, but that process of construction generates trash. So there could be several different reasons why this wouldn't be extrapolation. So this is one we'd want to look at the data a lot more closely to kind of make a determination as to where our good interpolation values would be versus where we're running into that extrapolation. All right, so we have another one here. And I'm going to have you go ahead and pause the video and give this one a try. All right, so we are looking at the growth rate of a child from 0 to 12 months, and we found their height in inches can be estimated using their age in years with a regression line of Y equals 9x plus 20. So it says, how tall will someone who is 8 years old be? Where X is measured in years, so I can substitute 8 in for X, and so we get Y is equal to 9 times the 8 years plus 20, and that gives me about 92 inches. Okay, and so in case you're wondering, that turns out to be 7 foot tall, 8 inches. So that is not very realistic for an 8-year-old, and so this is definitely falling in that situation of extrapolation. So really this 0 to 12 months is 0 to 1 year. So trying to use the data that we collected from somebody that was from 0 to 1 year old and then trying to predict something about an 8-year-old isn't going to work very well. And so that's why we're running into this extrapolation. All right, let's take a little more look at extrapolation, and we're going to revisit that ice cream problem. So extrapolations are suspicious because they require a very questionable assumption. And that assumption is that as the graph continues on, that relationship between X and Y stays the same. So in other words, that relationship isn't going to change when we look at extreme values outside of where our interpolation is. So with our ice cream example, we originally had that graph from about 12 degrees to 26 degrees, which is kind of this piece right in here. And yeah, that does make a really nice linear looking piece. If we collected more data from a wider variety of temperatures, what we might find is that as it gets colder, our graph is going to level out down here. It's just cold and most people aren't buying ice cream. There's also another really interesting phenomenon that as the temperature gets really, really hot, less people are going out. So less people are buying ice cream. My mom used to say, oh yeah, we can't get ice cream. It's too hot. It won't make it all the way back home on the drive. And so our ice cream sales are going to decrease here. So we end up with kind of this flat piece, the part that we've already looked at. Then we also have this downhill segment. So it is possible if we really define our interpolation well to just use a small piece of our graph that has a nice linear fit. But that's the reason we don't use X values outside of where our data points are. It's because we don't know what's happening outside of that area. All right, so with that in mind, our data has to be linear or fairly linear. It has to look reasonably straight in order to use this linear regression line.